Great. Okay. Well, thank you for having me here this afternoon. My name is Teng, and I'm currently a mechanical engineer at Lawrence Livermore National Lab. I did my undergraduate and graduate studies here in civil engineering at UC Berkeley, right here. And I did my master's research under the esteemed tutelage of Professor Khalid Masalam. So thank you very much, Professor. I'm going to talk about my master's research today. Professor Masalam with the PI. I also thank PEER for their technical support, as well as Caltrans. I thank you, Mr. Tom Shantz, for your support from Caltrans as well. This project was basically the development of a prototype that would measure the displacement using this vision-based system. And then we apply that to monitoring bridge settlements in the long term. So let's get started. First, I will motivate the problem, then discuss the solution that we came up with based on our review. Then I talk about the design we came up with, how we implemented it, then how we tested and validated it, and then finally things we could have done better. So first of all, a lot of these public agencies like Caltrans have a lot of infrastructure stock that they need to ensure work at a proper state of operation for the public good, right? Caltrans, according to their maintenance plan in 2015, had over 1,700 bridges that were backlogged in their system for maintenance and inspections. They estimated that across the next 5 years, they would need over $450 million to reduce that backlog. And furthermore, this need for inspections and maintenance will only increase as time goes on because these bridges are not getting any younger. Furthermore, on the other side of the problem, as these bridges are being designed by bridge engineers, these engineers have designed these bridges to anticipate certain loadings that they will see in their lifetime, one of which is differential settlement, where one part of the bridge settles more than another. They assume a constant amount of settlement that these bridges will incur, 1 to 2 inches, according to the Bridge Design Manual in 2015. And that might be conservative for a good number of bridges. A lot of these bridges may actually not see that amount of settlement, but this is a conservative approach to design. It could be reduced. Resources, money could be conserved if we maybe perhaps reduce these design factors, but we would have to understand settlement better. So if we understood settlement on a per bridge basis better, we could reduce design factors and then accept a small amount of occasional settlement as we understand it through the bridge's lifetime. So sure, we want to understand settlement better. We need to measure it somehow though. What is settlement? Displacement. How do we measure displacement? Traditionally, there have been a plethora of different sensors that people have used, but they may not be adequate for long-term monitoring applications. For instance, accelerometers, which are commonly used in lab settings, suffer from integration errors when you double integrate that measurement. However, one likely new technology up and coming that has promise for long-term monitoring application are vision-based systems. Essentially, you can imagine that there is a camera unit that is mounted on one part of the bridge, okay? And then it takes a series of pictures of another part of the bridge, and then in those pictures, it identifies a common feature in all of them and tracks the location of that feature through the photograph, representing its location through time. Now, what is that something that this camera is taking a picture of? It could be a physical target. It could be an actual big canvas that has a pattern painted on it and they mount it across the span of a bridge, perhaps. Or it could take a picture of just a common area. And in this area, it identifies some certain geometry, or maybe the threads on a bolt, maybe some nuts, and tracks the location of those features in the photographs across time. Indeed, from literature, this process results in fantastic readings, great precision and accuracy, sub-millimeter. However, certain things have kept it from being able to be deployed in the field for monitoring purposes. For instance, in many of these literature, the teams have used these really expensive, fancy cameras with really fancy and expensive telescopic lenses because you need to take high-quality images of something really, really far away. In addition, these are rather expensive, and they're kind of bulky too. You can't just leave them out in the field there and expect them to be there the next day. And also, a lot of these pictures that you take you have to process them somehow. So a lot of these researchers go out there in person, take the SD card, go back to their office and process it there. Not quite reasonable for trying to understand this large amount of data from many sites in a really efficient manner. And also, all these images need to be high quality, and they would note that a lot of light impacts, dust, would hamper the quality of the images. So this is what we proposed. We would substitute in place for an expensive camera, we have a little off-the-shelf commercial cheap camera. And to ensure that this thing is protected from the environment, we put it into a protective box. And then instead of taking, and now this is a cheaper camera, right? It can't take pictures of something far away too well. So instead of taking a picture of a target that's far away, we bring that target really close up to it. And instead of an actual canvas screen, we have a plastic screen that's partially translucent. Now this translucent thing has no pattern on it, so we have to have something on there to track the position of. We then proposed we have a camera mounted on perhaps the abutment of this bridge. On the other side of the span, we have a laser emitter that projects a beam across the span onto the plastic screen. So therefore, this laser beam imparts an image which we track. Now, this being said, this method perceives settlement, this is displacement, only as motion across this plastic screen. It has no notion of either the rotation of either the camera nor the laser unit. That would have to be tracked by something else, perhaps an accelerometer. Also, it only tracks relative displacement of one unit relative to the other because both reference frames are moving here. However, we want to take this thing that we come up to and shove it down the field. How do we do that? How do we design this prototype? First, we have to put in place some project requirements. And then we should have some sort of use case for the client that we can imagine that will drive the design of the prototype. And then we have to choose the hardware. How do we then control and make the hardware do things? We have to write some software for it. Then how do you power it? And then finally, how do you make it robust enough so that it can last out in the field? And I'll go through these questions in the remainder of this presentation. These are the requirements that we came up with. We wanted this unit, this prototype, to wirelessly transmit this data from the field to decision makers. We wanted these readings to be of sub-millimeter precision. We wanted the battery life to be at least of 1 year or better. These measurements should be taken at least daily. It needs to be rugged and also easy and convenient to use and install. This is the use case we came up with. You can imagine that as the engineer, you're going to mount this thing. You get this box, actually 2 boxes. You get the 2 units. They come pre-calibrated, and all you have to do is take it out there, mount it, align it a certain way, and boot it up. Once you boot it up, it begins in an idle state. Because you're not taking measurements right then and there, it's going to start in idle state, sleeping, low power mode. Then, when a measurement request signal is received by the units, they will wake up, do these measurement tasks, such as the laser unit will turn on, project the laser, the camera will take the picture, process that image, extract the data, and transmit it. Once that data is transmitted successfully, both of these units will go back to sleep and wait for their next request. This is the hardware that we ultimately used, the highlights of which are the Raspberry Pi, the Arduino, and the Adafruit cellular board. For those of you who may not be familiar with this technology, Raspberry Pis are essentially computers. They're like $45. And you can literally hook them up to a keyboard, mouse, monitor, and you've got yourself a fully fledged computer that can actually surf the web. Great stuff. The Arduino is cheaper than the Raspberry Pi, but it is a slimmed down computer. It's basically just a little processor. It can do simple computational tasks, read sensors, do simple computation. Well, it can do fancy things, but it's hard. Ultimately, we also need to figure out, okay, so these are the brains of the system. These do the thinking, these do the controlling, but you somehow need to transmit this information wirelessly. So that's when we have the cellular board. It's basically a slimmed down cell phone. It can receive text messages, calls, and everything like that, and you can program it to do what you want it to do. In addition, we have a Bluetooth transmitter and receiver because, hey, you've got a laser and a camera. They're far away from each other, but they got to talk to each other. The laser has to tell the camera unit, hey, there's a laser beam on you, please take a picture. These messages have to be passed somehow, and we chose to do it over Bluetooth. Then finally, we have this embedded system. We've chosen the hardware, but it needs to be tied together using some code, right? So I won't go through everything, but these are the highlights, if you will. I wrote some asynchronous code to enable the Bluetooth low energy communication we have between the 2 modules. This ensured that messages weren't lost, weren't dropped, and you can receive these messages as they come. I also didn't want any of these modules somehow failing catastrophically during a measurement sequence. If it encountered some sort of runtime error during this operation, I wanted to at least just recognize that there's an error, categorize it by some sort of error code, save the error code, and then just depending on the severity of that error, it may either proceed on, or it can take another path, or it can just take a final path and just shut down safely. We also wanted to make sure that any data that was not transmitted successfully, maybe the cellular signal out over there is not too strong. We want to make sure this data is not lost. So any data that was not saved, that was not transmitted successfully is saved into local memory and transmitted the next time a measurement is taken. Finally, power, right? We were talking about power. This, we needed to make sure that this device doesn't just die out there, right? And we did encounter some issues. For instance, the Raspberry Pi, being the more computationally powerful unit, consumes about 10 times more current, 10 times more power than the Arduino. Also, the cell phone unit actually had its own dedicated battery that needed to be charged to a certain threshold in order to have enough voltage to actually operate. And also we had a laser beam that when it's on, it sucks power too. So all in all, after doing some lab tests and trying to understand how much actual power all of these things actually consume, we estimated that the camera module needed about 4 amp hours of power every day, the laser 1.5 amp hours per day. And we had these solar panels and batteries on hand, and we estimated that we would need 2 solar panels to power, to supply enough power charged every day for the camera module, and 1 for the laser module. And we have these power banks to ensure that, let's say it's cloudy, suboptimal solar charging times, we have some backup power to supply energy for the system to operate. Once we had a prototype assembled, we did some testing. In a lab setting, we recognized that, wow, we did achieve sub-millimeter precision. We were able to achieve this precision at a distance of about 60 feet separation between one unit to another. And we also recognized that the tilting of the camera, I mentioned earlier that this thing has no notion of tilt, right, is actually non-trivial. It actually has a contribution to the perceived settlement reading. In fact, we can see that a pitch angle of about 5 degrees of the camera module will contribute about 5 millimeters of perceived settlement to the reading. So you have to account for that somehow, and indeed that's why we had accelerometers. Then putting it into a box. So we chose just a commercially available utility box. This thing had a NEMA 3R rating, meaning that the enclosure is protecting things against solid objects like dust and fingers and things. And also splashing and dripping water, rain, snow, the natural elements, as well as ice. So we also laser cut this clear acrylic that we could mount all of our hardware on in certain ways. So we have all our accelerometers and hardware mounted into this acrylic cradle, if you will. We drop this into the box, bolt it all together, make sure it's still. We close the box, seal it up, lock it, and boom, you got a box that you can shove in the field. And that's exactly what we did. We put it underneath a bridge here on UC Berkeley campus. You can see the camera and the laser unit there mounted underneath the bridge, and you can see in the top right corner, we have a measurement being taken. In the foreground, you can see the laser beam that's being projected across the distance to the camera. And on the bottom, you see the solar panels that were mounted on either side of the bridge for charging purposes. And indeed, we had this thing mounted out there for about a week. Granted, more data would have been great, but that was just the project timeline. We deployed it for about a week, and we recognized some limitations. We did see that the 2G signal underneath the bridge was rather weak. There was a lot of vegetation. The bridge was wood and big I-beams, and so sometimes the signal was rather weak down there. Also, we did notice that while the camera enclosure was able to keep away things like transient light artifacts, like maybe one car coming by and flashing their lights on it. It could not protect against steady state disturbances. For instance, reflections of the laser beam itself on the water, onto the screen, or even perhaps just direct sunlight right on the screen as well. These things did throw off readings, But all in all, across that week, we did recognize that, hey, we were able to basically measure a baseline constant of no position change, which is to be expected because this thing, nothing was going to happen this week anyways. These are the three outliers that we have on the plot here are from the aforementioned issues that I had mentioned about light artifacts. As far as next steps go, we can divide them up into two categories, improvements on the prototype we developed and long-term directions. First and foremost, more testing would have been great, of course. There's no such thing as too much data. We could have reduced power consumption a lot. We could have tried to extend the intermodule range. We could have improved the remote communication of the device. Instead of 2G, why not use something like 4G that all of our phones use now? We could have also added more accessibility features for the prototype. And of course, this thing is pretty big, pretty heavy too. We could have reduced the form factor a lot as well. Long-term directions, we could definitely try to investigate ways of trying to mitigate ambient light impacts on the image feature extraction. We could also try to explore different laser options. Instead of a crosshair, which is what we use, we could use 4 dots maybe. Also, we could try to incorporate that accelerometer data much more effectively. We could try to perhaps correct the displacement measurements with these tilt readings. And lastly, I need to give credit to the team that I work with. I worked with Albert, Wyeth, and of course myself. Albert is a current undergraduate here in UC Berkeley. He's studying computer science and cognitive science. And Wyeth is currently in the structural engineering master's program. And with that, that is the end of my presentation. Thanks.